These are the newest images of 3i Atlas from the Mars Reconnaissance Orbiter, and I'm pretty sure this is actually the most disappointing revelation we've had about this object. Because after weeks of waiting for NASA to release the high-resolution images that could have settled the debate once and for all, what we got instead raises more questions than it answers. On November 23, 2025, 3i Atlas once again appears to be veering toward Mars. And something strange is happening with Atlas all over again. James Webb once recorded Atlas skimming frighteningly close to Mars before its trajectory suddenly shifted cleanly away with no explosion, no massive dust cloud, nothing that could explain the maneuver, as if an invisible hand had nudged Atlas aside at the last moment. So in this video, I'll break down the disappointing truth about what actually happened during 3i Atlas's Mars contact, what the images reveal, and more importantly, what they don't reveal. Let's start with what we were expecting. On October 2nd, 2025, 3i Atlas flew by Mars at a distance of approximately 29 million kilometers. That's about 0.19 astronomical units, or roughly 18 million miles. In space terms, that's actually quite close. Orbiting Mars at that time was the Mars Reconnaissance Orbiter, equipped with the HiRISE camera, one of the most powerful cameras we've ever sent to another planet. HiRISE can resolve features as small as 30 centimeters across on the Martian surface from orbit. When pointed at distant objects, it can capture details that Earth-based telescopes simply cannot see. So when 3i Atlas passed by Mars, NASA made the decision to turn HiRISE away from Mars and point it at the interstellar visitor. This was a rare opportunity. The viewing angle from Mars was completely different from Earth's perspective, allowing us to see the three-dimensional structure of the object and its jets in a way that wasn't possible from a single vantage point. The astronomical community waited and waited and waited. For more than 6 weeks, the images remained unreleased, and when they finally came out, what we saw was both revealing and deeply frustrating. The HiRISE images show 3i Atlas as a bright central nucleus surrounded by a complex coma structure. Multiple jets are visible extending away from the nucleus in different directions. The resolution is better than most Earth-based observations, but it's not the crystal-clear definitive image that many were hoping for. Here's what we can see. A single bright nucleus, meaning the object has not fragmented into multiple pieces. This was one of the key questions. Many scientists expected 3i Atlas to break apart due to the enormous forces created by its jets. But the HiRISE images confirm that as of October 2nd, the nucleus remained intact, a complex coma with different structures. The cloud of gas and dust around the nucleus shows asymmetric features, with brighter regions in some directions and fainter regions in others. This suggests that the jets are not uniformly distributed around the nucleus, two tails pointing in opposite directions. One tail points almost directly toward the Sun, measured at about 106 degrees, while the Sun was at about 115 degrees. This is the anti-tail we've been discussing, a rare but not impossible feature. The other tail points away from the Sun in the normal direction at about 301 degrees. And here's the critical observation. The imaged region showed no hint of fragmentation. The astronomers who analyzed the images specifically wrote in their report that they found zero evidence of any breakup whatsoever. But here's where the disappointment comes in. The images don't show us the level of detail we need to answer the most important questions. The resolution, while better than Earth-based observations, is still not high enough to resolve the nucleus itself or see fine details in the jet structures. We cannot see the surface of the nucleus. We cannot determine its exact shape or size with precision. We cannot see whether there are distinct active regions or vents where the jets originate. We cannot measure the width or collimation of the jets at their source. Most importantly, we cannot see the perpendicular jet in the detail we need. Remember, one of the most significant anomalies is the jet pointing 90 degrees to the Sun direction, something that should not be possible with natural solar heating. The HiRISE images confirm that this jet exists, but they don't show us enough detail to determine what's producing it. The images also don't show us any obvious signs of artificial structure. There are no geometric patterns, no reflective surfaces, no antenna-like protrusions. If 3i Atlas is a technological object, it's not revealing itself in these images, and perhaps most frustratingly, the images were processed and released with minimal enhancement. The raw data shows a relatively faint object against a dark background. More aggressive processing could potentially reveal fainter structures or details, but NASA has not released those enhanced versions. Let's talk about why the fragmentation question matters so much. When we first observed the massive jets coming from 3I Atlas, we calculated how much material the object would need to be losing to produce those jets. The numbers were staggering, approximately 50 billion tons of material per month, but the object itself was estimated to weigh only about 33 billion tons based on its size. This created an obvious problem. How can an object lose more mass than it weighs? The only logical explanation was that the object must be fragmenting, breaking into multiple pieces that each have more surface area exposed to sunlight. This is exactly what happened with Comet Shoemaker-Levy 9. When it broke apart in 1992, the total amount of material it released was way more than what we thought the original comet weighed. But that made perfect sense once we realized it had broken into 21 different pieces. More surface area means more ice exposed to sunlight, which means more outgassing. So when we saw 7 jets on 3I Atlas and massive multi-million kilometer tails, the natural conclusion was that the object had fragmented. It was the only way to make the math work, but the high-rise images say otherwise. The object is still single, still intact, still producing enormous jets without breaking apart. This brings us back to the fundamental problem. If 3I Atlas hasn't fragmented, where is all the material coming from? How is a solid object losing more mass than it weighs? Let's revisit the numbers because they're important. To produce the observed jets and tails, 3I Atlas needs to be losing about 50 billion tons of material per month. That's not a guess. It's calculated from the brightness and extent of the tails and the known properties of cometary dust and gas. For that much material to sublimate from ice, the object would need about 1,600 square kilometers of surface area absorbing sunlight. That's equivalent to a sphere about 23 kilometers across, but Hubble measured 3I Atlas at only 5.6 kilometers across. The math showed us it needed to be 4 times bigger than what it actually was. So we have 3 possibilities. 1, our estimate of the object's size is wrong. Maybe it's actually much larger than 5.6 kilometers, and we're just not seeing the full extent of the nucleus. But Hubble's measurements are generally reliable, and multiple observations have confirmed the size estimate. 2, the object is losing mass at a rate that should be impossible for its size. This would require some exotic mechanism we don't understand, maybe unusual porosity, maybe internal heat sources, maybe something else entirely, but this pushes the boundaries of known physics. 3, the jets aren't being produced by normal sublimation. They're being produced by some other mechanism, maybe technological thrusters, maybe plasma interactions, maybe something we haven't thought of yet. This is the most radical explanation, but it's the one that some researchers are taking seriously. Now let's talk about the trajectory shift that happened around the time of the Mars encounter. In the opening, I mentioned that James Webb recorded Atlas skimming frighteningly close to Mars before its trajectory suddenly shifted cleanly away. Let me clarify what actually happened. In early trajectory calculations, 3I Atlas appeared to be on a path that would bring it uncomfortably close to Mars. The projected footprint of Atlas stretched across Mars like a thin grey bruise on the plots. Impact probabilities were still low, but the projected path was concerning enough that engineers were watching closely. Update after update, the tracking loops tightened around 3I Atlas. Each new observation shaved the error ellipse smaller, and instead of drifting away from danger, Atlas seemed to hold the risky corridor as if following an invisible rail. This was unusual. Normally, as we get more data, the uncertainty decreases and the predicted path changes, but Atlas kept pointing at Mars. Then, over just a handful of solution cycles, the line began to tilt. Without any obvious flare from Atlas, without a surge in brightness or a sudden dust fan, the nominal path of 3I Atlas eased upward, lifting the corridor clear of the Martian limb. The object simply never hit Mars. Photometry teams combed the data for signs that 3I Atlas had paid for the change with a violent outburst. The light curve showed the usual flutter of an active body, but no huge spike, no blooming plume that could justify a precise, well-timed shove. To the flight dynamics groups, the residuals around 3I Atlas shrank obediently as the new path settled in. The natural explanation for this trajectory shift is straightforward. Our early trajectory calculations were based on limited data. As we gathered more observations, the calculations became more accurate. What looked like a close approach to Mars in the early data turned out to be a safe flyby once we had better measurements. This happens all the time with asteroids and comets. When a new object is discovered, the initial orbit calculations have large uncertainties. Sometimes the early calculations suggest a possible Earth impact, which makes headlines. But as more data comes in, the uncertainties shrink, and we realize the object will miss Earth by a comfortable margin. With 3i Atlas, the same thing happened with Mars. The early calculations suggested a close approach. The later calculations, based on better data, showed a safe flyby. There's nothing mysterious about this. It's just how orbital mechanics works when you're dealing with limited data. The fact that we didn't see a massive outburst during the trajectory shift is also not surprising. The shift wasn't a sudden change in the object's actual path. It was a refinement of our understanding of the path. The object was always going to miss Mars. We just didn't know it at first. But here's where the natural explanation becomes less satisfying. The object did undergo measurable non-gravitational acceleration. This is confirmed by multiple independent analyses. The acceleration was small but real, and it did alter the trajectory by a measurable amount. Non-gravitational acceleration is common in comets. As ice sublimates and gas escapes from the surface, it creates a rocket-like thrust that can change the comet's trajectory. This is well understood and has been observed in many comets. But here's the problem with 3i Atlas. The amount of non-gravitational acceleration observed suggests that the object should be losing a massive amount of mass. We're talking about roughly 13% of the object's total mass over the course of its journey through the inner solar system. When a comet loses that much mass through outgassing, it creates a huge debris cloud. The gas and dust expelled from the comet should be visible as a bright, expanding coma. We should see it clearly in images and spectra. But with 3i Atlas, the expected debris cloud is missing. The space around 3i Atlas stayed relatively clean. There was no unambiguous, blinding plume to match the required billions of tons of material. The acceleration was real, but the expected debris field was missing, like a footprint without a corresponding weight. This is the paradox that keeps coming up with 3i Atlas. The object is doing things that require massive mass loss, but we're not seeing the mass loss we expect. Either our models are wrong, or something else is going on. Now let's talk about why the high-rise images took so long to be released. The Mars flyby happened on October 2nd, 2025. The images were captured around that time, but they weren't released until mid-November, more than 6 weeks later. During that time, speculation ran wild. Some suggested that NASA was withholding the images because they showed something extraordinary, clear evidence of artificial structure or behavior. Others suggested that the images were being carefully analyzed and processed to extract every possible detail before release. The truth is probably more mundane. Processing and analyzing spacecraft data takes time. The HiRISE team has a backlog of images to process from their primary mission of studying Mars. Taking time to point the camera at an interstellar object is a special request that requires additional work. The images need to be calibrated, processed, and analyzed before they can be released. The team needs to write up their findings and prepare them for publication. All of this takes time, especially when the team is working on multiple projects simultaneously. But the delay did fuel suspicion. When images take weeks to be released, people start to wonder what's being hidden. And when the images finally come out and they're not as detailed as expected, the disappointment is amplified. So what did we actually learn from the Mars contact and the high-rise images? First, we confirmed that 3i Atlas has not fragmented. As of October 2nd, the nucleus remained intact. This rules out one of the main explanations for the massive jets, that the object had broken into multiple pieces with more surface area. Second, we confirmed the existence of the anti-tail and the complex coma structure. The jets are real, they're pointing in multiple directions, including toward the sun, and they're creating structures that extend for millions of kilometers. Third, we confirmed that the object passed Mars safely. There was no collision, no close encounter that would have disrupted the object's trajectory. The Mars flyby was a distant observation opportunity, not a gravitational interaction. Fourth, we learned that even with a spacecraft in the right position with a powerful camera, we still don't have the resolution we need to answer the most important questions. The high-rise images are better than Earth-based observations, but they're not good enough to see the details we need. And fifth, we learned that the mass loss paradox remains unsolved. The object is still producing jets that require more mass loss than we can account for, and we still don't see the debris cloud we expect. So why is this disappointing? Because we had high hopes for the high-rise images. We thought they might provide the smoking gun, clear evidence one way or another about what 3I Atlas really is. If the images had shown clear signs of fragmentation, it would have supported the natural comet explanation. We could say, okay, it broke apart, that's why the jets are so massive, mystery solved. But they didn't show fragmentation. If the images had shown clear signs of artificial structure, geometric patterns, reflective surfaces, antenna-like protrusions, it would have supported the technological hypothesis. We could say, this is definitely not natural, we need to investigate further, but they didn't show artificial structure either. Instead, the images show an object that looks like a comet but behaves in ways that comets shouldn't behave. It's intact but losing too much mass. It has jets pointing in impossible directions. It survived perihelion without breaking apart. And we still don't have a satisfying explanation for any of it. The disappointment isn't that the images disproved any particular hypothesis. The disappointment is that they didn't provide the clarity we were hoping for. We're still stuck in the same place we were before, with an object that doesn't fit any of our categories, and a growing list of anomalies that demand explanation. But there's still hope. The Mars contact was just one observation opportunity. The next major opportunity is the Jupiter encounter on March 16, 2026. And this encounter is potentially much more significant than the Mars flyby. At Jupiter, we have the Juno spacecraft, which has been orbiting the planet since 2016. Juno has cameras and instruments that could observe 3I Atlas during the encounter. The viewing geometry will be different from Earth, providing another three-dimensional perspective on the object. More importantly, the Jupiter encounter is at a gravitationally significant distance. As we discussed in previous videos, 3I Atlas will pass within 35,000 miles of Jupiter's Hill radius, the boundary where Jupiter's gravity becomes dominant. This precision is statistically improbable for a natural object. If 3I Atlas is going to do anything unusual, release probes, change course, activate systems, the Jupiter encounter is when we would expect to see it. This is the optimal location for deploying objects that would remain in stable orbits around Jupiter. The observation window is from March 9th to March 22nd, 2026. During this 2-week period, we need to have every available telescope pointed at 3I Atlas. We need continuous monitoring, multiple wavelengths, and rapid analysis of any changes in behavior. The Jupiter encounter is our last chance. After this, 3I Atlas will be heading out of the solar system, getting fainter and harder to observe. If we don't learn what this object is during the Jupiter encounter, we may never know. So what should we be demanding from NASA and other space agencies? First, full transparency. If there are additional high-rise images or enhanced versions that haven't been released, we have a right to see them. This is a discovery that belongs to all of humanity, not just a select group of researchers. Second, dedicated observation campaigns. We need to maximize observations between now and the Jupiter encounter. Every telescope that can point at 3I Atlas should be doing so. We need to build the most comprehensive dataset possible. Third, Juno observations. NASA needs to task the Juno spacecraft to observe 3I Atlas during the Jupiter encounter. Even if it means interrupting Juno's primary mission for a few days, the potential scientific return is enormous. Fourth, rapid data release. When the Jupiter encounter happens, we need the data released quickly, not 6 weeks later, not after months of internal analysis. The global scientific community should have access to the data as soon as it's collected. And fifth, serious consideration of a probe mission. If we act quickly, we might still be able to launch a spacecraft that could catch up to 3I Atlas after the Jupiter encounter. We have the technology. We've done it before with comets. The question is whether we have the will. Folks, the disappointing truth about 3I Atlas's Mars contact is this. We waited 6 weeks for images that we hoped would provide clarity. Instead, we got images that confirmed the object is intact, confirmed the jets are real, but didn't provide the resolution or detail we need to answer the fundamental questions. The object is still producing jets that require impossible amounts of mass loss. It's still pointing jets in directions that defy natural explanations. It's still on a trajectory toward Jupiter that shows statistical precision that should be impossible for a natural object. The Mars contact didn't solve the mystery. It just confirmed that the mystery is real, and now we're running out of time. The Jupiter encounter in March 2026 is our last chance to study this object in detail before it leaves the solar system forever. We need transparency. We need dedicated observations. We need to take this seriously, because whether 3I Atlas is an exotic comet, a plasma phenomenon, or an artificial probe, it represents something extraordinary that demands our full attention. If you watch to the end, drop me a like and subscribe for more encounter, and why the next 4 months are the most critical period in this entire investigation. I'll see you in the next one.